In this live video, we're going to focus on automated titration. Now, I know in 114, we probably spent 2 to 3 months on titration. It was titration after titration after titration after titration after titration after titration. I know it. I know. The last thing that you want to do is another titration. But you know, if you took 115, we did a few titrations, but we didn't do very many of them. If they were involved in a monograph, then we probably did some. But that was about it. So they were scatterbouts, and they were kind of hit or miss. And depending on what monographs we picked, we could have did quite a few, or we just probably did 1 or 2, and that was it. So for those people that have taken 115 and not 114, then folks, this is a way that we can titrate, and we can do it in a more automated fashion. That's what this lab is all about. For those of you that took 114 and 115, I guess, if you've taken the 114 class with all of the manual titrations that we included, then there is a chance that we didn't do a lot of the automation, and this is the class that we will focus on automation and maybe quite heavily, or at least give you some time one-on-one with the machine without anyone breathing down your neck. That's what this is all about. So we want you to go to the instrument. We want you to go through the motions of calibration. We want you to standardize using the machine. We want you to titrate some samples using the machine. And that's, folks, about it. All right, nothing more than that. So with that said, I want you to think of this as almost like not a lab, but a training exercise. That's what this is all about. So there's going to be very little math work. There's going to be very little spreadsheet work. It's more or less just going through the motions of using a piece of technology that we have in the laboratory environment that will make our lives a little bit easier if we're lucky enough to work for a company that has an automated titrator. All right, so first off, for those of you that are unfamiliar with titrations, so before we go further in the titration discussion, you've got to know that there's plenty of different types of titrations that are out there. Now, it seems like most of the time, we are going to focus on acid and base titrations. And guys, this is probably one of the most common types of titrations that's performed in a laboratory environment, but it's not the only one. And in this experiment, with the introduction of an automated titrator, we are still going to focus on acid and base titration. So we're not going to deviate from that, but it's often one of the very first types of titrations that you are introduced to when you're taking a laboratory course. Another one is a Carl Fisher titrator known as a KFT. Yeah, these can be done manually, but they're so difficult to do manually. You've got to have a piece of equipment nowadays in order to do that. So that is most of the time now just regarded automatically as a titrator that will do the job for you. And it will take over and it will titrate the sample and it will do what it needs to do. So Carl Fisher titrator is Carl Fisher titration is all about the percent water. Now, keep in mind, we use this for percent water specifically, not percent moisture. Moisture and water is different. So if you're determining how much exact water is in the sample, then Carl Fisher titration is one of the few things that can do that for you. Next up, the other type of titration, or another one, is called a precipitation titration. And one of the most common ones is a Moore titration. That is just the name that's given to the setup for the titration. And the Moore titration is all about determining chloride. And you're probably wondering, well, chloride? Well, isn't all chloride soluble? How is this a precipitation reaction? Well, yeah, it is. If you look at the solubility chart, all chlorides are soluble except for, and it gives you a couple of different versions, that chloride or a salt of chloride will not dissolve in water. And one of those choices is actually silver. So what happens in the precipitation reaction is we've got a burette, and inside of the burette we have silver nitrate. So that is a solution that we have prepped. We know the concentration of the silver nitrate, and hence we know the concentration of silver. And then as silver nitrate adds to the sample that has chloride in it, what goes on is a single replacement. So silver leaves the nitrate and goes to the chloride, and AgCl is actually going to be a solid, so it begins to precipitate out of solution. So what happens is that there are less and less and less and less chloride in the actual sample that I'm titrating, and then sooner or later there'll be no chloride left in the sample that I'm titrating, and that's a sign that all of the chloride has now made a precipitate with the silver in the titrant. So there are many other versions of precipitation titrations. This is just one of them. And then what we can use here for the precipitation is actually a chloride probe or something similar. So it will tell us how much chloride is there, and we titrate until there's no more presence of chloride at all. And then we can use the milliliters of the titrant and the strength of the titrant to figure out how much chloride was in the sample from the very get-go. Next up is a redox titration, and that redox is actually two halves of the same story. One is reduction and one is oxidation. So what we're looking for here is loss of electrons and gain of electrons. We're looking at electron movement. So what happens is that in this type of titration, we've got a sample, that's one half of the story. We've got a titrant, that's the other half of the story. And then when we mix them together, and again, not really acid and base here, but when we mix them together, we see a transfer of electrons. Electrons leaves one thing and goes to the other one, and we get some differences in the chemistries and the structures and how the electrons move and where do they go, and all of this can be titrated. So, again, just like before, you use the concentration of the titrant, you use the milliliters of the titrant to get the amount of moles of titrant that was required. But if you know that, then you can equate that to the electron count. If this is how many moles of titrant there was, then this is how many electrons were needed for the reaction to go to completion. And then if we can backtrack that, we can then figure out how much was in the sample. So again, same concept. It's all about finding a concentration of an analyte. That's what this is all about. That's what all of these are about. And an analyte is just something or stuff that you're trying to find in solution. That's just a fancy word, and that's all that means. Next is a complexometric titration. And that complexometric titration, if you look at the word, you see the word complex. So this one is not acid-base. This one really isn't precipitating out anything. This one's really not a redox reaction either. Electrons are not leaving one thing and going to another, but a complex is being formed. So one of the examples here that I have is EDTA. And EDTA works great for calcium and magnesium, which then equates to water hardness. So for the EDTA molecule, I want you to think of as having 4 fingers, and those 4 fingers will be dripped down into a solution that could have magnesium or that could have calcium. And what goes on is that if calcium is present, calcium is there, it's swimming around in solution, EDTA comes in and catches that calcium, and it wraps its little nasty skeleton fingers around the calcium, and it pulls it out of solution. So we can actually monitor how much EDTA that it takes, and that amount of EDTA is kind of proportional to the amount of calcium and magnesium that's in that solution, and then we can calculate the water hardness that's in the sample because of that. So again, not really acid-base, not really water titration, not really precipitation, no electron losing and electrons gaining, actually. It's just really the cage type of system that EDTA works upon. And that cage will create a complex, and of course we call this a complexometric titration. Next up, and our final one that I'll talk about at least in this video, is a back titration. And what happens is that in a back titration, you've got a sample that you need to be titrated. And this sample, the chemistry of it can be very slow. That's one of the reasons that we use a back titration. So as we are titrating that sample, drip, 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 wait for the color change, wait for the color change, wait for the color change. It just takes forever in order to turn color. So because of that, and we don't want to kind of bypass that color change because the reaction takes so slow and it needs some time to catch up with us. So because of that, what happens is that we just wham in the very beginning. So we add a excess of either an acid or a base. So for instance, let's say that in this particular titration, this is a base that I have in my Erlenmeyer flask that I'm getting ready to titrate. So that base, let's say, is a very slow solution. It takes a little bit of time, it's sluggish, and by the time I add in another milliliter or 2 milliliters, that stuff is still working on the previous mill or 2 mils, and I don't want to wait forever for this titration to finish. So a back titration really kind of helps us with this problem. So if I've got a base, and again, it's just an example, then I will add excess acid. And what happens is that because I just wham all of it at one time, what I now have in the end before I get ready to titrate is extra acid that is left over. So all of the acid has completely, in this case, neutralized the base. It's all gone. All of the acid has been used up that was needed, and then I have a little bit of extra that's left over. So I need to make sure that I add enough of it. That's why we call it excess, but I'm going to add enough of it in order to just completely neutralize this sample completely out from the very get-go, completely out. That way I don't have to rely on a sluggish reaction to change color. I can then go to maybe a more traditional kind of titration of an acid at base and maybe some phenolphthalein indicator, and then drip, 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 and then I get my color change and it's instantaneous and I go stop, and then I write down the milliliter. I mean, that's what this is all about. So this extra acid is then titrated, and that titration is giving me the extra. So if I know the total that I added and I subtract the excess that was determined by the extra that was determined by the titration, then I can calculate how much was actually used. And if I know how much was actually used up in this step, then I can calculate how much base was there in order to use that up, again in this example. That is a back titration. So you are, in a way, over titrating it, even though you didn't titrate. You just swamped it with the corresponding acid or base. And all of that was neutralized, and all of that was used up in the very first step. And then you're backtracking to figure out how much was actually used by determining the excess. Again, I like to explain this as a pizza party. So I order 12 pizzas for the pizza party, and then I let everyone just eat whatever, and then at the end of the party I look down and there's 2 pizzas that are left over, and I'm thinking, okay, well, if I have 2 that's left over, then that means this crazy bunch of people ate 10 pizzas throughout the course of the night. Okay, so that is a back titration. I'm looking at how much is extra, and if I know how much I started with, I know how much is used up, and that's exactly what goes on here. All right, just as a review, and again, you might need it, you might not, but this is an example of a titration, of course. So what happens is that in the beginning, I will pipette a solution, and that is a very key step. You've got to pipette. And the reason is because you have to make sure that you are adding the appropriate amount of sample and you're keeping track of these volumes very carefully. Now, I know if it's a solid, you measure that out, and you measure that out on a balance and you keep as many decimals as you can. But a lot of times these are solutions that we are working with. And if we are working with a solution, do not pour those into a beaker to titrate. And do not pour those into a graduated cylinder to then go into an Erlenmeyer flask to titrate. Those, as we have talked about before, are not as accurate as a pipette is. So with a pipette, this is your best chance of determining the exact volume that you are using in this experiment, and you'll get better numbers. So we're going to be pipetting, and after we pipette, most of the time we add an indicator. A few drops is needed, hardly anything else. So 2 to 3 drops. Sometimes they give like a half of a milliliter. Okay, whatever, we'll add a half of a milliliter. But it's just really enough for you to visually see a color change with. That's all that we're after, and very often it takes a very tiny amount in order to do this. So a few drops most of the time is going to be okay with an indicator. Next up, we have a burette. The burette does not need to start from the very, very top. I mean, you just fill it with titrant. As long as you get the initial reading of that burette, then you'll be perfectly fine. So I'm starting at 10 mils, I'm starting at 0 mils, I'm starting at 12.4 mils. Whatever the case is, that's up to you on how you want to handle your titration. But do not feel the need to fill it all the way to the tippity top, especially if you know it's not going to take a lot of volume in order to get that titration completed. All right. Next up, after you do the initial reading, then you drip, 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 drip into the Erlenmeyer flask that's down below. All right. So as you drip, 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 you'll see volume is getting used up of your titrant. And then finally you'll stop when, ta-da, the indicator changes color. That final reading we will record, and we do the difference. So we'll take the final and we'll minus the initial, and that will give us our total volume that we needed for that titration to take place. That total volume is going to be used in the calculation, so it's very important for you to record as close as you can to the true volumes that's inside of these burettes. Also, the smaller the burette, actually the better it's going to be, because smaller burettes will often be divided up into smaller tick marks or smaller units. So if I get a really big burette, 50 mils or 100 mils, my readouts might be in 0.2s, right? 20, 20.2, 20.4, 20.6, 20.8, and then 21. If I get a smaller burette, those tick marks are typically divided up into smaller chunks or smaller markings. So now I could maybe measure 20.1, 20.2, 20.3, 20.4, 20.5, 20.6, 20.7, 20.8. You get my picture. All right. So often we go smaller, as small as possible. But in our lab, we normally have 50 mils stock burettes. That's what we use most of the time, and we get pretty good numbers when we begin to titrate with those. But in a real life, real laboratory setting, if your titration is going to take 10 milliliters or less, why are you using a 50 mil burette? You can use a 10 milliliter burette or smaller, depending on how many mils that it takes in order for your titration to go to completion. Next up, another piece of review that I want to talk about is what we call a titration curve. So this curve is representing what happens in a solution as far as pH goes along the course of the actual titration. So here in the very beginning, you're going to see at spot number 1. Spot number 1 is before the titration begins at all. So this pH is like a pH of 3 maybe. I'm just going to estimate it. And that means that this thing is probably an acid. So I'm titrating an acid. And if I go up here to the title of the graph, look, weak acid. So we are titrating a acid with a base. And I know that because when I put my pH probe in there, my pH probe ran a pH of 3, and that's on the acid side of the house, not on the base side of the house. So I've got this acid in a flask, and then I drip, 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 drip into the flask a base. And I'm going to go slow most of the time, but it's not going to take all day. I've got other things to do, right? So I'm going to drip, 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 drip until I feel really comfortable when I start to see a color change, and then I'll slow down tremendously. Once I see a color change start to become evident and linger around a little bit longer, I slow my titration down so that way I can be ready for it when it does turn color. All right, so that's station or spot number 1. So as I begin to drip, 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 What goes on is that I am gradually increasing the pH in this case, or in this example. So I've got an acid in the flask, and I'm slowly adding base. And that solution is getting more and more basic. It's not a lot, but it's getting more and more basic. And that's what I'm seeing here on the graph. So I started with a pH of 3, and then it goes up across pH of 4, and then it goes into a pH of 5, and then it's going to continue to increase little bits at a time until it goes, wham, up it goes. And that is at spot number 3. So what happens in this area? Why the drastic change? And that's because at this particular point of spot number 3, we call this very often the equivalence point. And that equivalence point is where, in our case, the concentration of the acid is equal to the concentration of the base, or the number of moles. So the number of moles of acid that are present in my sample is equal to the number of moles of the base that I've added to the sample. So if it's a one-to-one relationship, they're exactly equal, and when they kill each other out, then I see a pew on the titration curve. And because the next drip that goes into the flask, I'm titrating with a base. So what happens is that that little drip goes into the flask, and pew, up it goes as far as pH is concerned. Because I'm titrating with a base, my base has a pH in this case, maybe greater than a 7. And now I'm drastically seeing that on the titration curve. So if I go over, I now see I'm at a pH of 10, I'm at a pH 11, I'm at a pH of 12. And then if I continue the titration after that, pew, then what I'm doing is I'm just adding extra base. That's all that I'm doing. It's not really killing each other out because there's no more acid that's left over in my sample. So as I add more and more base, I slightly get a little more and more basic in this case, and therefore my pH slightly goes up, little bits at a time. So that drastic jump is called the equivalence point. And that equivalence point is normally where our color changes happen with indicators. So what happens is that if we know that our equivalence point is going to happen like a pH of around 8, or a pH of 9, or pH of 7, what goes on is that I figure out where that's going to be, and then I choose an indicator that will turn color around that equivalence point. So a traditional acid-base type of titration often uses phenolphthalein as an indicator because phenolphthalein has a pH change of around 7 to 8-ish, somewhere in there. And these indicators are pretty good if they're plus or minus 1 from where we need to target. So, of course, the closer you are, the better it's going to be. But at the same time, you don't want to pick something that's so extravagant that it's going to cost an arm and a leg in order to order it. Well, titration curves can go backward as well. There's no difference here. So here is a titration curve, and this titration curve starts at spot number 1 at pH of like 11. So that means that this is a base for me. And I know that it's a base because my pH is very high. So this is where I'm starting in my flask. And if it's a base, then in the burette, I need an acid. And I need to drip, 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 drip the acid into the flask over a course of time. And when I do that, that acid is killing out that base, little bits at a time, little bits at a time. So what happens in the beginning is my pH begins to go down little bit by little bit by little bit. It goes and it continues to go until the acid gets a little bit closer to eliminating all of the base. And when the acid gets closer to eliminating all of the base, then whoop, down it goes. So that's at spot number 3. That's also what we call an equivalence point. There's no difference there. And that equivalence point is telling me this is the time where the amount of acid is equal to the amount of base. So therefore they are equivalent. And that's why we call it the equivalence point. And hopefully we'll find an indicator that will change in that realm in some form or fashion. If we continued with the titration after that, then not a big deal. I'm now on the acid side of the house. The acid has taken over. The acid has now plummeted that pH below a 7. Here we're working at pH of 2 or 3. And then as I add a little bit more acid, 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 I start to see this pH go a little bit more acidic and acidic. All right. One of the problems I think that people have, though, is the titration math. If you're given the equation, then it's not a big problem, right? People can plug numbers into a template and crank out a number using a calculator. But what if you had to come up with this value on your own? This is where people normally struggle a little bit, and that's where problems with the titration math begin to happen too. A couple of things that you need to know: the titration is always, the math-wise, is always kind of the same steps. So very often you will need to know the concentration of the titrant that you have put into the burette. So let's say 0.5 molarity, all right? And then we also need to know the milliliters of titrant that was required in order to get my color change. Okay, well that comes from your titration. You did this, you did that step, you did the test, you wrote down those numbers. So how many mils did it take? Oh, it took 10 milliliters. Okay, great. So what begins to happen here is that the template or the model for a titration calculation is you first start with molarity equals moles over liter. And you know the strength of the base that you used in the titration in this previous example, and that was 0.5 molarity. So we also know the amount of milliliters that it took. And this equation for molarity, though, it's really formatted for liter, not milliliter. So we've got to convert our milliliters into a liter. And we do that by dividing by 1,000. Milli is a millennium. Millennium is 1,000 years. So there's 10 mils. Therefore, we'll divide that by 1,000. And what we will end up getting is a 0.0010. All right. No, hold on. Look, I'm trying to do the math in my head, and look at what I'm doing. All right, so here's the trick. 0.1, that would be 100 mils, not 10. So we're going to move that over twice. So there is our 10 milliliters in terms of liter, 0.010. All right, so now that you've got that template, what happens is that you'll take 0.5 and you'll multiply by 0.01 and you'll get a value. And that value is the moles of base or moles of acid or moles of titrant, whatever you've decided to use. It doesn't matter. This is kind of what we do first. And then you'll need to know a little bit about the stoichiometry. Very often, these are one-to-one ratios, so there's nothing that you have to do with those if they are one-to-one ratios. But you need to know a little bit about the stoichiometry before you make that decision. So a balanced chemical equation is going to be very important. So in my example that I'm going to give you, the moles of base equals the moles of acid. Let's say it is 1-to-1. And in this example, it will be 1-to-1. So whatever mole you get for your base when you do this on the machine, that's how many moles of acid are present in the sample that you brought to the table. Once you determine that, you're a little bit closer to the final step. You have the moles of acid now. And really what happens after this point is, what does the titration want? So if it wants the grams, then that's fine. You use the formula weight to calculate the grams of sample that was present in your sample, or grams of analyte that was present in your sample. Very quick. Take the moles, multiply by formula weight, and you get the answer in terms of gram. If you want milligram, then times it by 1,000, and that will give you milligram if that's what you're after, right? It just really depends on the titration. Sometimes they want molarity instead. So if you get molarity, if you've got moles of acid, well, look, molarity equals moles over liter. So if I've got the moles of acid, ching ching, I've got that number on top. And then for my liter, let's say my direction said, you pipetted 25 mils a sample. Okay, 25 mils, that goes into here, so 0.025. So that is the volume amount of the sample that you used in the test. 25 mils, 10 mils, 5 mils, 100 mils, 50 mils, you get it. I mean, that's what goes on. So if I know moles of how much was there, and if I know the total volume that I used, well, moles divided by liter, that is terms of molarity, and that is a concentration of the sample that I titrated. So many different routes that you can go to It really just depends on the type of test that you're running and what that titration is really asking for. Is it grams? Is it milligrams? Is it molarity? Is it percentage? I mean, the list just goes on and on and on and on and on. And hence why very often in a real working environment, they will give me a template. And that template will be typically a spreadsheet. And I'll just 5.4 mils, enter, and then and then I get the number and I just print off the spreadsheet, or I write down the number that this Excel spreadsheet has done for me. So it's as simple as that, but very often it's important to know where these numbers are coming from. All right. Okay, so before I go on, I think I need to pause and give you a break. This was just a general overview of a titration, so a titration curve and a little bit about the math that goes on and the idea of a titration. And in the next video, we're going to talk more about the automation part. So how do I get away from the manual titrations, and how do I use equipment and instrumentation in a lab to make my job maybe a little bit better, a little easier, more automated, so quicker throughput, which means process more samples in a timely fashion. That's what we're going to focus on in the next video when we come back. So with that said, I'm not done yet, but if you need a water break because you worked up a sweat over this lecture material, then go take a sip and then come back. I'll be ready.